So, I'm Richard Steenbergen from GTT. We're going to talk today, again, for anyone who hasn't seen this before. It's been about 4.5 years since I did this talk, so I'm doing it again slightly revamped, so hopefully it'll be slightly different than what was there before, hopefully slightly more informative. But we're here to talk about a practical guide to correctly troubleshooting with Traceroute. So, quick introduction. Troubleshooting problems on the internet, number one go-to tool is Traceroute. Every OS comes with it. There's a million different websites you can run traceroutes from. There's looking glasses, there's visual traceroute tools, there's things that'll put a little pretty picture together and show you where the latency goes up so that everyone and their grandmother can and does use it. There's a lot of free stuff, there's a lot of commercially available tools, there's a lot of tools like MTR that'll run continuous trace routes that'll kind of map out the network and give you some visualization. And it seems like it's a very simple and easy to use tool. All you do is you type in a destination IP address and it shows you the path to every router along the way. And it would seem intuitively like you could look at this and see something really obvious like, hey look, the latency jumps up here, or hey look, there's packet loss here, and that would actually help you go figure out the problem. But it turns out not to be the case. So why does that turn out not to be the case? Well, these days most modern networks are actually pretty well run. So a lot of your simple issues like simple congestion or routing loops or random things that are easily diagnosed with Traceroute tend to be less and less common. What you're left with tends to be more and more complex. And it turns out there's very few people that are actually skilled at interpreting a traceroute. Like I said, it looks relatively easy to use, but it turns to give people the impression that they know how to read a traceroute when they don't, or that they can look at a single traceroute and make a determination. And the reality is you need more than one traceroute, and you need some knowledge of the destination endpoints. You need a bunch of other things that are outside of that one piece of screen input to actually figure out what's going on. So in reality, it turns out most ISP NOCs and even most mid-level IP engineering staff aren't actually qualified to interpret traceroute correctly. What this tends to do is you get an overload. Anyone that's ever answered NOC tickets from Traceroute gets an overload of stupid Traceroute tickets for things that are not your network. And it tends to really, number one, make it difficult to troubleshoot real issues. Number two, make it difficult to report real issues to other people because people don't believe you when you send in a Traceroute ticket that you actually know what you're doing. So sample traceroute output for anyone who hasn't seen a traceroute. If you haven't, you've bigger problems than I can help you with here. You know, you're going to see a list of rows. You're going to see the hop number, the IP address, and the reverse DNS for what that router hop is, and you're going to see a series of latency measurements. In this case, we're seeing 3 latency measurements per hop. So if you actually want to know how traceroute works at the packet level, here's what's happening. You are starting by launching a probe packet toward the destination, and you set a TTL value, a time to live value, on the IP header of 1. Every time a router touches a packet, it will decrement the value, and when the value hits 0, it drops the packet. And more importantly, it sends back an ICMP message to the original source that says, hey, I dropped your packet. And Traceroute looks at these ICMP messages and uses that to figure out the path. So when you launch that first packet with a TTL of 1, the router gets it, decrements the value, hits 0, now it's going to drop the packet. Drops it, sends back its ICMP TTL exceed message. The source gets that ICMP, calculates the difference in time between when it sends its probe and when it gets this ICMP response, and displays a hop and a latency value. And go back to step 1, repeat. But this time increment the TTL value, so start with 2. So the packet will get 2 hops out before it gets dropped. The ICMP goes back and you use that to figure out what your path is. And then when you get to the end, typically what will happen is you'll get most traceroute probes are either UDP to a port that nothing's listening on, or an ICMP message or something. So you'll get back a different ICMP message other than a TTL exceed, and that's how Traceroute knows, hey, we're done, stop. Some more details about how this actually works. Most implementations send multiple probes per hop. So like I showed in the previous example, the default is 3. So that means for every time the TTL value is incremented, you're going to send 3 probes, and you're going to get 3 different latency measurements for each hop. Each probe packet uses a unique key to distinguish itself. So typically what you'll see there, most traceroute implementations, like a UDP-based traceroute, will have an incrementing destination port. So when it sends 33434, it knows that it's probe 1. When it sends 33435, it knows that it's probe 2. That's how it reconstructs the data when it gets back. But another thing to keep in mind is that every probe packet is a completely independent trial. So just because Traceroute is showing it to you on the same line in the same place with the number 1 beside it, doesn't mean that it in any way followed the same path either forward or backward. And this may or may not be visible to the end user. So it might look like it's the exact same path, it might be the same router address, it might be the same everything, but you are in no way guaranteed that the path the packet actually followed is the same path. Everything is a completely independent trial. The way the traceroute calculates latency is very simple. Like I said, you timestamp when you launch the probe packet, you timestamp when you get the ICMP packet back, and you subtract the difference, and that's your round trip time. There is no router-based processing of the packets themselves. So the router doesn't do any calculation, the router doesn't have to have an accurate clock, the router doesn't do anything other than drop the packet, send the ICMP back. Some implementations will actually encode inside the payload of the probe packet. They'll encode a little bit of data, and when you get the ICMP message back, you'll get the first few bytes of that. So sometimes they'll use that to offload some of the state, so they don't have to keep track of when they sent the probe packet. But it's the principle is the same. You're taking the difference in time between when you sent your packet and when you got your packet back. So, like I said, the latency is the total of the time taken for you to forward that traffic to that hop where it gets dropped, the time that it takes for the router to drop the packet and generate the ICMP message, and then the time that it takes for that ICMP message to get back to the sender. Those 3 elements come together to make up your latency value. So if you look at Traceroute and you want to know what are you actually seeing, what hops are you seeing, what interface IP addresses are you seeing, Traceroute will always return the ICMP packet sourced from the ingress interface. So we look at this example, the probe packet comes into router 1 and it has an ingress interface with a /30 on it, and it is 172.168.2.1/30. When it drops the packet, when router 1 decrements the TTL to 0, decides that it's going to drop this packet and sends back an ICMP message, it's going to source that ICMP from the interface that it came in on. So in this example, you see the 2 hops that you'll actually see in Traceroute, the 172.168.2.1 and the other ingress interface for router 2. You're not going to see the egress interface, you're not going to see the return, you're not going to see any of that. An interesting factoid is this is actually not a standard behavior. If you actually go read the RFCs that say how a router should work when they drop a packet and send an ICMP, it actually says that it must be sourced from the egress interface. And it turns out this doesn't happen in practice. And if it did, Traceroute wouldn't work. So we're kind of fortunate that no one ever fixed it, but interestingly, no one ever went back and updated the RFC. So, next thing we want to talk about is how you interpret DNS in a traceroute. Really, you don't read traceroute by the IP address. Most operators are kind enough to throw some DNS information in there. Some of them aren't. Google. But most of them are, and it's very helpful for figuring out what's going on. Even if it's not your network, you can kind of get an idea of a lot of information like geographic locations, where these things are physically located. You can start to tell the interface types and the capacities. You can even start to tell the router types and roles. And most importantly, you look for network boundaries and relationships. So why do you want to know the location of the routers? Knowing the geographic location of the routers is important for figuring out a lot of things like, is this suboptimal routing? Am I going from Phoenix to Ashburn to come back to San Jose? That matters, and so you need to know if the router's in Ashburn or Los Angeles. It's going to help you figure out your network latency. You're going to, we'll talk about this later, but the latency is largely tied to the distance that the signal is propagating over, and so if you see something that is vastly out of the way, then it's probably not a good thing, or that might or might not be an explanation for the latency that you see. So the most commonly used location identifiers that people put in Traceroute are the IATA or the ICAO airport codes, or SILI codes, primarily in the US. But a lot of times people just attempt to abbreviate it to a common. Population, there's an airport, and they have a unique set of codes assigned to them, so it's very easy to reuse those codes, especially if you have a small number of large pops. So for example, if you care about Phoenix as a major airport, PHX is very easy to figure out. If you care about mapping into a lot of smaller detail, like say Chandler, Arizona, where we're at, it's not so important, not so useful to you. But if you really care about the major metropolitan areas, then it's a good way to do it, and it's a short 3-letter code. Sometimes things get confusing though. A lot of airport codes are not intuitive. You would get into a couple situations. So for example, somewhere like New York is served by 3 different airports, JFK, LGA, and EWR. So a lot of times people will just write NYC. And that is actually a code that represents all 3 of those. But a lot of times you get into a situation where it's not clear which airport am I closer to, what level of detail should I go into that. And then the other one that you see is a lot of airport codes are based on historic names. For example, Northern Virginia is served by IED. Which is not immediately obvious. Dulles Airport, that's not immediately obvious that that's Northern Virginia. So sometimes people just write it out as something like WDC or something else that's easier to identify for the layman. Silly codes are common language location identifiers. These are the kind of things that you see when working with telcos. There is a gigantic database maintained and sold by Telcordia. And like I said, typically used by telcos to do lots of identifying down to the rack level, down to the panel level. There's a standardized code. The part that we care about for Traceroute purposes are the first 6 letters. It's called the geopolitical identifier. So for example, Houston, Texas, or Ashburn, Virginia will be written out as these 6 letters. This gives you a much broader coverage. So if you really do care about the difference between Phoenix and Chandler, you're going to want to go to this type of a code. But the issue there is that this is really a US specific thing. Sometimes you'll see other people kind of adapting it for use outside the US, but it's not a standard there. You can't go to a book and consult it and figure it out. And then sometimes people just make stuff up. Another example of an airport code that's not obvious, ORD. If you don't live there or fly through airports a lot, you might not know that O'Hare is Chicago, or Midway is the other airport. You might not know that either one of these are Chicago, and so you might just find it easier to put CHI. I mean, the benefit there is that it's more of a human readable value. So if it's a US person reading a traceroute going through the US and it's really obvious that it's in the US, CHI might be fine. But if it's a non-US person and the traceroute is not obviously in the US, like conveniently located between New York and San Jose or something like that, then it might not be obvious what that means, and that's where it's nice to use actual standards. So I have a little table of the commonly used major cities, broken down by airport codes, silly codes, and just some of the other codes that people will use in practice. So for consulting offline. Here's some of the non-major US cities, same type of thing. The major peering points, the major interconnection points that you typically see. Next big thing you can do with interpreting DNS is identifying interface types. So most networks will be kind enough to put their interface information into DNS too, and it helps you figure out if it's a 1 gig or a 10 gig or an OC3 or something hideously small or hideously large. Kind of helps you figure out what's going on with the network. You should be careful to make sure that the network you're looking at actually keeps their DNS up to date. There's a lot of people that set their DNS manually once and then they go reuse the IP 4 years later and don't update it, and so it's still pointing to something wildly bogus. Most large networks actually use automated systems to generate their DNS updates. Certainly we do, certainly most other large networks do, and it's easier for everyone if you're managing thousands of interfaces to keep that information up to date. So here's an example of how you can look at the information given in a traceroute and kind of figure out something about the device. So this was an example that came up on a traceroute XE1110 on a device called Edge 1, New York 1, level 3. I have a chart on this later, but you know that XE-number/number/number is a Juniper format for 10 gig. You know that the device has at least 12 slots because we're already on slot 11. You know that it's at least a 40 gig per slot router because you're into more than one PIC in the slot. So you know at this point that it's a Juniper MX960 because there's no other device out there that could fit this profile. And so if you have an idea of what hardware people are running, it really helps you figure out architecturally what's going on, how to troubleshoot stuff. So it's good to know those things. Here's a full breakdown of the naming conventions, everything from your FastD, your GigE, your 10 gig, and how it looks in Cisco IOS, XR, and Juniper. So the next thing you want to know when looking at DNS is what is the role of the router. Really why this matters is you can figure out if it's a core device, you can figure out if it's an edge device, a peering router, and that'll kind of help you figure out, number one, it'll help you figure out where the network boundary itself is. So as you find that boundary, that'll become more useful in troubleshooting later. But number two, it'll help you just in general figure out what's going on with this traceroute and who do you contact when there's a problem. So some of the common identifiers that you'll see, core routers will be called CR, core, gigabit backbone router, converged core router, Ethernet backbone router. That one's slightly confusing because it looks like it might be an edge router, but it's not. You look for your peering routers, which are often called your borders, your edge, your internet routers, your gateway routers, or not necessarily gateway routers, but your peer devices. And then typically your customer devices tend to be called things like ARs, AGRs, customer access router, high-speed access, or just gateway. Anything that says gateway is typically a customer demarc point. And then the next thing that you can identify from DNS is network boundaries. So network boundaries are especially important to identify because they let you figure out where policy changes occur. So for example, once it crosses this boundary from my network to your network, your policies probably change because you pay different amounts to different carriers and have different local pref settings. And so you're very likely, once that packet crosses that border, to have a different reverse path, for example. So identifying network boundaries is important for that reason. It also tends to be the area where things go wrong. It's a lot easier for me to have capacity to myself than it is for me to call up a third party and negotiate capacity and order cross connects and do all that. So typically the choke points tend to be those demarcs with third parties. And the type of relationship you're looking for, it's typically either going to be a transit, a peer, or a customer. And most networks are nice enough to try and put something in there to indicate that it's a customer demarc so that you know what's going on. So in this example, it's really easy to spot where the DNS changes. Your first hop says global crossing. These are old slides. Your second hop says Sprint. And so it's pretty obvious that this is the demarc point. The other thing you can look for is when the remote party is in the name. So for example, in the next example, hop 4 is a global crossing router. And hop 5, hey look, it's the same router, but this one says Cogent on it. So typically what that means is the /30 was allocated out of one party's IP space. So for example, Global Crossing gave the /30 to this interface and didn't bother to contact Cogent and say, give us DNS information for your side. So they just put in Cogent dot and then the same device on the other side. So that's really how you can figure out that type of thing. And then the easy way to verify that is just to look for the DNS on the other side of that /30. So you see .90 is this Cogent IP address. So let's look at .89, the other side of the /30, and you can see the interface and the device that it lands on. So now you have an idea if this traffic is staying on this device. If it's not, it'll help you on troubleshooting later. Next big thing you need to identify in Traceroute is the latency that it reports. So to understand the network latency, there's really 3 primary causes of network-induced latency that we care about. The first one is serialization delay. That's basically the delay that occurs when you are encoding the data from packet form into a string of bits and putting it on the wire. There's queuing delay, which is the delay that happens when the router or switch is holding onto the packet, not transmitting it, waiting for an opportunity to do so. And then there's propagation delay, which is just how long it takes the electromagnetic signal to transfer over the wire or fiber or whatever the media is. So serialization delay. In networking, serialization just means the process of encoding the chunks of data onto the wire. The faster an interface is, the faster this will occur, and it's completely linear. So the math is very simple. You just take the packet size and divide it by the link speed. So for example, a 1500 byte packet sent over a 1 megabit link, your first step would be to convert the units. So 1 megabit is 1000 kilobits per second, which is 125 kilobytes per second divided by 8, which is just written out 125,000 bytes per second. And then you can take your bytes divided by bytes per second and figure out that it will take 12 milliseconds for this 1500 byte packet to serialize over the interface. So why does this actually cause a delay? Remember, the packets move through the network as an atomic unit. You can't transmit the first half of the packet now and come back to the rest later. You generally can't start transmitting the packet until you finish receiving it. That's true of most routers. There are some switches, some low latency switches that use what's called a cut-through architecture. So after they get the first 64 bytes, they start forwarding the packet. But those tend to be specialized. You tend to lose features when you start to do that. And it's the kind of thing that you'll only find in like specialized low latency switches. You generally don't find that in routers. So because you can't start transmitting until you finish receiving the packet, if it takes 12 milliseconds to go across the wire, that's 12 milliseconds that you've added to the total latency of this conversation every time you touch a packet-aware device, every time you touch a router or a switch. So fortunately, this is a lot less of an issue than it used to be on modern high-speed networks. The reason for that is interface speeds have gone up many orders of magnitudes over the many years that the internet has been around, but packet sizes have pretty much stayed the same. So it's getting less and less of a problem. But if you've got a low-speed link, this can still be a very noticeable cause of latency. So probably not an issue on your 10 gig link where it causes 0.0012 milliseconds of latency, but it might be an issue on your 768K DSL line where you just cause 15, 16 milliseconds of latency just to pass the packet across because it is a packet. And interestingly, it also makes a good counter-argument to a lot of the kind of popular we should deploy jumbo frames everywhere arguments out there, because when you do that you actually increase the latency, you increase the amount of contention on the link, and you potentially increase jitter. We'll talk about that later on. So queuing delay, the next cause of network latency. Queuing is, like I said, when the router or switch is holding the packet in memory, waiting for an opportunity to transmit it, but not actually doing so. And every moment that the router holds the packet in its memory, not doing anything with it, your latency is going up and your user experience is probably going down. So why do we need queuing in the first place? Well, first we need to understand how link utilization actually works. So typically when someone says, I've got a 10 gig port and I'm doing 5 gigs over it, they might say that's 50% utilized. That's actually not true. At any given moment, the interface can only be in one of two states. It can either be transmitting, in which case it's 100% utilized and you can't do anything with it, or it's not transmitting and it's 0% utilized. So what you're actually saying when you say 50% utilized is 50% as measured over 1 second. So you pretty much need some queuing for an interface to function. And if you ever doubt that, ask anyone who's ever bought a top-of-rack switch that doesn't have enough packet buffers and tried to get line rate performance out of it. So when is queuing a good thing? You need queuing especially when you have mismatched interface speeds, especially if you've got a higher speed interface sending to a lower speed interface. So like we talked about under serialization, the packet comes through the interface at a certain speed based on the speed of the interface. So a gig-y link will transmit that packet 10 times faster. It will get through the interface 10 times faster than a fast-y will. So if you've got a bunch of gig-y ports feeding a bunch of fast-y ports, even if you're in no way maxing out the utilization, you're going to have these packets come in a millisecond before they're ready to go out. You're going to need buffering. The other area that you tend to need buffering is when you've got a lot of talkers. So for example, if you've got a top-of-rack switch with 41 gig ports going down to servers and they're all feeding into a couple of uplink ports, you have a large number of talkers feeding into a smaller number of ports. And it may not even matter that the interface is faster. You've still got all these packets coming together at once. So you've got these little micro bursts and you need to queue for. So technically speaking, queuing always increases throughput. And if you think about this logically, the longer you hold on to the packet, the more opportunity you have to find a slot to transmit it when the router is not used. So then the question becomes, how long should you hold on to it, and what's the value there? So typically you might see something like, if you are willing to buffer the packet for an extra 5 milliseconds, you could get a link utilization up from 60% to say 85% before you start seeing drops. That's probably worth doing, but it depends on your application. So when is queuing bad? Well, as an interface becomes more and more full, the amount of time that you have to hold on to the packet to find an open slot to transmit it increases exponentially. So you might still be able to successfully deliver every packet. You might be able to get a full 10 gigabits across this 10 gig link, but you might have to hold every packet in the buffer for 5,000 milliseconds to do it. It's probably not a good thing for your end user, not for anyone who's watching video or voice or SSH or anything interactive, and it's really going to interfere with TCP performance too. So at a certain point, queuing actually becomes counterproductive. And the question is, what is that point, and how do you know how to configure it? Because like I said, if you get an extra 1% throughput, but you have to screw up the latency on all of your traffic to do it, that's probably a bad thing. Typically, what most people see with normal internet mixed traffic is once you get above about 95% utilization, as measured over 1 to 2 seconds, you're going to start to see almost all of your packets noticeably affected with significant latency. So you really want to keep it ideally below 90, but the lower the better. If you keep a link at below 50%, you'll see perfect, no jitter, no nothing, and everyone will have a good time. And it turns out that most routers actually have really bad defaults for their interface queues too. There's a lot of kind of overreaction to things like, oh, we shouldn't ever drop a packet, or, oh, I heard that this carrier grade router needed bigger buffers and I paid a lot for it, so it should have really big buffers. And so sometimes people ship routers with buffers that'll hold packet for 5 to 10 seconds, not milliseconds, while it's looking for a slot. That's just too much. That's excessive. So there's a lot of research that's going into this right now. If you Google for the term buffer bloat, you'll find a lot of further documentation on this and kind of why you don't want that. But when you're looking at a traceroute, when you see a 5,000 millisecond time, you kind of know what's going on. It's not because there's a 5,000 millisecond fiber path unless someone ran fiber to the moon and back. It's because it's being stuck in a router queue. And then the third cause of latency is propagation delay, which is simply time spent on the wire. So if you want to look at the math of this, it's really simple. The speed of light in a vacuum is roughly 300,000 kilometers per second. And it turns out that's not very fast over long distances, so you start to see measurable latency. If you want to look at how fast light propagates in fiber, fiber is made of glass. It has a refractive index of around 0.148 in the core. So 1 divided by 1.48, you see that light propagates through fiber at around 2/3 the speed that it does in a vacuum, about 0.67 C. So it's roughly around 200,000 kilometers per second. If you expand that out, 200,000 kilometers per second equals 200 kilometers per millisecond, and then you would want to divide that by 2 to account for round trip time. So if you see a 1 millisecond in your traceroute, because you're measuring the time there and the time back, that means there's roughly 100 kilometers of fiber in the way if all you're looking at is propagation delays. So just as an example, if you were to go all the way around the world on the equator, come back to where you started from, just from speed of light delays through fiber, it would take you about 400 milliseconds. So that's how big the world is, and certainly you can have fiber paths that are not straight. So how do you look at a traceroute and identify what latency is affecting you and figure out if it's normal? Your first step is to use location identifiers to figure out the geographical information and figure out if that kind of fits what you're looking for. So for example, you have a packet that's NYC, New York, and it's going to LHR, that's London, and you see that it's about 67.6 milliseconds for 4,200 miles. Yeah, that sounds about right. That's actually one of the better fiber paths you can get. And then this other example, you see the latency go up between AT&T and Cogent. If you look at the geographic information, you see AT&T, Washington, D.C. And then you see Cogent IED, which is also Washington, D.C., and you see the latency went up 220 milliseconds. That's probably not distance related. That shouldn't happen. So that's either the return path or a congested interface. But you don't know for sure until you look at more data. So the other thing that starts to affect traceroute is prioritization and rate limiting. So remember that I said the traceroute latency is actually the sum of three things. The time that it takes for the probe packet to get to the router that's dropping the packet, the time that it takes for the router to drop the packet and send its ICMP, and the time that it takes that ICMP message to get back. Number 1 and number 3 are actual real network characteristics, but number 2 is completely artificial and only happens on traceroute packets. So what happens there is you tend to have routers get busy one way or another and either drop the ICMP generation, not do it at all, in which case it looks like packet loss in the traceroute, or take a little bit of time to get around to generating that ICMP message, in which case it looks like high latency. But this is, again, completely artificial. It doesn't affect real traffic, it only affects traceroute traffic. To understand this, you have to understand what's called to it versus through it. So most routers have a distinct processing path. What these are called, the data plane is what you call for packets forwarding through the routers. And inside the data plane, there's two paths actually. There's the fast path, which is what the vast majority of your regular, ordinary, everyday internet porn goes through. That's just forwarding through an ASIC that is very good at doing hundreds of millions of packets per second. And then there's the slow path, and that handles anything that is an exception. Some common examples of that are if there's an IP option configured, that needs to get handled separately. If you need to do ICMP generation, which is where traceroute falls into. If you have configured logging, if you've configured sampling, if you've done anything on your router that requires special processing, it has to punt it to the slow path. And then the control plane is traffic that's actually being forwarded to the router. This is completely different than traffic that goes through it. So some examples of that are your routing protocols, your BGP, your IS, your OSPF, your SNMP, your CLI, when you telnet and SSH to the box, when you ping the box itself, when you ping from the box, when you ping to it. Anything that goes to an IP address that is actually configured on the router. This also includes things like ARP, as the router is doing ARP, anything that the router itself processes and doesn't just forward. And it turns out that most router CPUs are actually relatively underpowered, so it's not uncommon to find a 300 to 600 gig router that has a 600 megahertz CPU holding the whole thing up. These things are old and cranky and tend not to have the best software on them either. And remember that ICMP generation is not a priority for the router. Of all the things that it can be doing, that is probably the least important to actually keeping the network running. So that's going to affect your traceroute. On some platforms, the slow path data plane actually shares the same resources as the control plane. So what that means is if I get a packet that I have to TTL drop and I have to punt it to a CPU to handle the ICMP generation, that runs on the same CPU as the guy that's SSH into the box doing a show IP BGP. So what happens is someone goes in and does a big complex regex show IP BGP, and it slows the CPU down so much that it takes a while to generate the ICMP message, and now you start to see latency that doesn't really exist in the traceroute. Probably one of the most common infamous examples of this is called the BGP scanner process. So classic iOS, every 60 seconds there's a process that runs that iterates through every BGP route in the box to kind of do some back-end cleanup. And every 60 seconds when it runs, it makes your trace routes look like crap. The other thing to keep in mind is that most ICMP generation is going to be rate limited. There's a lot of reasons that you could need to generate an ICMP. It's not just TTL exceed. Could be anything from a destination unreachable, a route just flapped. It could be that you've created a routing loop. It could be any number of things. And it's a very complex process that gets handled in software by a general purpose CPU. And so there's no traceroute ASICs out there. There's no FPGAs that do any of this. And these CPUs are also doing other things, and they're doing other more important things like keeping the routing protocols from timing out and letting you do your show IP BGP and processing your ARP, doing all that type of stuff. So you actually wouldn't want your TTL 0 packets to be completely unchecked. anytime someone creates a routing loop, if you route a thing to me and I point the route straight back to you, that's going to create a routing loop. That's going to give you a flood of TTL expiring packets. So if you spent all your CPU time dealing with those and generating ICMP, number one, you generate a huge flood. You might actually be DDoSing someone in the process. Number two, you'd be consuming all your resources. So most routers tend to have a rate limit. The problem there is these tend to be wildly varied by vendor, platform, software, and are many times not configurable and not logged. So you might get into a situation where you've got a big core router somewhere and 10 different people decide that they're all going to run MTR at the same time, maybe because of an actual network issue that went away, and that's now so many TTL exceed messages that your router is not processing them, and you're going to start to see artificial loss, and everyone's going to start to see this, and they're all going to start to open traceroute tickets with your NAC. So here's how you can figure out if there's an actual forwarding issue. If it's actually an issue, the loss and latency will persist across all future hops. So if you look at this example here, number 2, you see this weird spike from 18 milliseconds to 68 milliseconds. But you see how it doesn't continue in hop 3 and doesn't, I cut the rest, but it doesn't continue anywhere else? That means it's not a real forwarding issue. If it was actually in any way congesting or having a bad route or whatever, you would see that follow all the way through. If you don't, you know that it's completely cosmetic. That's the number one thing to look for, and that tends to take out about 50% of your random people on the internet sending you traceroute complaints about high latency. And it's just a particular CPU spike that's not cosmetic, and if you run it again, it'll probably go away. When in doubt, you can also try other things like a non-TTL expiring method. So if you were really curious about the latency to hop 2, you might just ping the IP directly. It's going to be handled differently, but that might be a way to just kind of measure that again and again and see if you're getting the same behavior. The other thing that you need to be careful of in traceroute is asymmetric paths. So remember, what Traceroute is showing you is actually the forward path. You are seeing how your probe packet goes to the destination. What you are not seeing, and which makes up half the latency value, is the return path, which can be completely different and is completely invisible. So at no point can you ever look at one traceroute and guarantee that you know the answer. You need to look at a minimum of 2. You need to look at the forward and reverse paths before you even begin to have a hope of figuring it out. Like I said, not only is the reverse path completely hidden, it can be completely different. You have no way to know. So asymmetric paths tend to start at network boundaries. That was why I said that it was so important to identify the network boundaries earlier, because that's where the administrative policies change. So look at this example, and you see that global crossing to Sprint, you see a network boundary, and you see Ashburn on one side and Ashburn on the other side, and the latency has gone up 100 milliseconds. So that could be two things. It could be that the global crossing side is congested to Sprint, but you don't know that for sure. You don't know that until you look at the reverse path, because it could also be an asymmetric reverse path. In this particular example, what happens is as soon as it hits Sprint side, Sprint has a different local policy on which path they're going to prefer, and it returns via a different path. It goes back via a cogent path that's congested, and that's what's causing your 100 milliseconds of latency. But you can't see that in this traceroute. So again, you always need more than one traceroute to identify this type of thing. So what do you do when you've got an asymmetric traceroute and the end user or whoever you're working with hasn't sent you 2 paths? What are some ways that you can kind of try to rule this out? The most powerful thing you can do is to work with your source address. So in this example, let's assume that you're multi-homed to global crossing on level 3, like I said, old slides. You know that global crossing reaches you via global crossing, and Sprint comes back to you via level 3. So you think that there's a problem between Sprint and level 3, but how do you prove it? How do you know for sure? What you can do is run the traceroute from your router and set the source address manually and set it to the /30 that is given to you by your transit provider, in this case global crossing. And typically the way this works is the provider always gives the customer the /30. That's the 99% of the time what you'll see happen, and peers tend to kind of go 50-50. So in this case, because it's a /30 that comes out of Global Crossing's aggregate, it's going to follow that routing behavior. So it doesn't know that you're multi-homed to level 3. It only thinks of itself as a Global Crossing IP. That's going to force the reverse path to come back from Sprint to Global Crossing. And if you see the latency go away, then you can guarantee that, or you can deduce that the problem was between Sprint and level 3. So another thing to remember about asymmetric paths is that they can happen anywhere, can and will, especially on networks with multiple exits. So here's an example of a very simple peered network, a network that peers in 3 locations: Washington, D.C., Chicago, and San Jose. And typically the way routing works is people do hot potato. They want to get the packet off their network as quickly as possible and get it to the other party. Number 1, because that reduces their costs, and number 2, because the destination network tends to have a better idea of where they're forwarding the traffic than you do. They carry all their own de-aggregates and do their own traffic engineering, and it's generally a good policy to get the packet to the destination as quickly as possible. So in this example, on hop 1, you see the reverse path. It goes across this interface in Washington, D.C., and it comes back across this interface in Washington, D.C. On hop 2, you see the reverse path is different. Now it actually comes back via Chicago. On hop 3, the reverse path comes back via San Jose. And this can happen at every hop along the route as you change where your reverse path is. So you can't take a latency hop in the middle of a trace route for granted, because it might be showing you, for example, hop 2 has a spike and hop 3 doesn't. It could be cosmetic, or it could be that the Chicago return interface is congested and only the Chicago return interface. So that's the kind of thing that you would want to probe further, run some more trace routes, see if it's consistent, see if it's the same behavior or not. So how do you use source address in your trace routes? What if it's numbered out of MySpace, as in the case of a peer? You can still see some benefits. Typically what I tell people to do is start sourcing from as many different diverse sources as possible and see what you can get. So for example, say that I peer with level 3 and we have a /30 between each other, and it's my /30. So I can't set it to their side and hope that it all just works out, because it's not. It's going to follow my routing policy. It's part of my aggregate. What actually might happen is a lot of networks tend to carry their edge /30s in their IGP. So that /30 in particular, because it is an edge interface to a peer, still gets carried in their network and still forces it to act as though it was their route. So there's always some benefit. Try it from a whole bunch of different viewpoints and see if you can deduce what's going on. Another thing to keep in mind is that a lot of routers have different default source addresses. Typically, the default on most routers, if you configure nothing, is to set the source address to the egress interface that the probe leaves from. That may or may not be what you want. In fact, it's probably oftentimes not what you want, but maybe it is. If you can configure other options. For example, Juniper, you can configure system default address selection, and that will always source the packets from your loopback address. So that'll be a lot more consistent, if nothing else. You might still want to go back to looking at individual egress interfaces to do some deduction, but most of the time you probably want to be consistent, so you don't randomly wonder why this one path is higher than the other, and it turns out to be a reverse path issue every time. Another big thing that affects traceroute is multipaths and load balancing. So remember, like I said at the beginning, every probe is a completely independent trial, and most traceroute packets, the UDP and TCP traceroute probes, use a different layer 4 port every time, so they know which probe they're on: hop 3, hop 4, probe 1, probe 2. Because they use a different layer 4 port every time, what tends to happen is the equal cost multipath algorithms that are hashing on the packet and figuring out how to distribute across multiple paths are looking at these as different flows, and that they could send them different ways. So here's an example of a very innocuous multiple path. You see it goes across 2 different routers within TLA every time, 1, 2, 1, 2, 1, 2, and that's purely just, it's incrementing the port by 1, and so it's going 1, the other, 1, the other, 1, the other. That one's very easy. Two of the probes go over one path, one goes over the other, and you can see that there's 2 parallel paths at layer 3. Slightly more complex example, the paths don't always have to be equal. So here's an example of what looks like a potentially confusing trace route, but what's actually happening is you have two parallel paths. One that goes Ashburn, New York, Seattle, one that goes Ashburn, Chicago, Seattle. And these are both perfectly fine, valid paths that could work great, but it's very confusing if you don't know what you're looking for. And then the worst the worst multiple path scenario you can get into is unequal lengths. And this is really confusing to the traceroute reader because it tends to make it look like someone's going back and forth, back and forth. So say, for example, there's a load balancing situation where there just happens to be an extra router X inserted in the path. And otherwise, these are equal cost, and it's going to load balance between the two. And traffic's going to flow fine. But what you're going to see is a traceroute that goes BCB, DCD, EDE, and it's going to look confusing as all hell. So keep in mind when you see something like that, that's often what's going on. When in doubt, if you want to take it down to something slightly less confusing, just configure your traceroute to only do a single probe. So for example, in the Unix traceroutes, the command is -Q1. For whatever reason in the Juniper CLI, you can do this from the shell. So if you drop this shell and do a traceroute manually, it'll work, but it's not actually in the CLI. So minor annoyance. But remember, this may not be the actual path that your traffic forwards over, and every probe is still an independent trial. So you're not guaranteed that you're seeing one contiguous path. You're not guaranteed that you're seeing the one side of that two-sided load balance. You're seeing one particular string, but it might bounce back and forth between the two. And in fact, it probably will. Other things that you can do if you suspect that this is an issue is look at different IP addresses. Sometimes people have their hashing configured to look at IP addresses. So if you see a weird path .3, try trace routing to .4, .5, .6 and see if it does different things. That's usually a pretty good way to kind of narrow in on when it's one path out of a 64 path bundle or something horrible like that. That's probably the worst thing you could ever try and troubleshoot, but that's a good way to identify when something like that's happening. And then the other thing that pops up in Traceroute is how it works with MPLS. So remember, there's a lot of large networks out there that run completely MPLS-based cores, and some of those devices don't even carry an IP routing table, which they're doing it for cost reasons or for performance reasons or whatever. And it's perfectly fine. You've got an MPLS-based core. It doesn't need a routing table. But what this means is it causes a problem for how the ICMP is generated. Because if you don't have a local routing table in your core device, how do you know how to send the ICMP message back? So the workaround for this is called ICMP tunneling. What this does is, if the router is forced to generate an ICMP, rather than do a routing lookup and forward it like a normal router would, it puts it back inside the LSP that the packet was coming in on, and forwards it all the way to the tail end, which is perfectly fine for getting the messages delivered, but it makes the trace routes look really weird. So here's kind of a diagram explaining that. Instead of the previous model where at hop 1 it would return, at hop 2 it would return, at hop 3 it would return, now every hop along the way it's going to forward that packet to the very tail end of the LSP before it comes back to you. It tends to make your trace routes look something like this. So here you've got a port between Global Crossing and AT&T, Palo Alto to San Francisco. It's probably a local regional port, and you see the latency jump up quite a bit. But you see the latency stay consistent the entire way through. As it goes from San Francisco to Chicago to New York, the latency stays exactly the same. And what's happening there is ICMP tunneling. When that hop number 3, that router in San Francisco drops the packet, rather than returning it to the source in San Francisco, it puts it back in the LSP and it forwards it to New York before it can return. So if you see something like that, you kind of have an idea of what to look for, and don't get confused by it. So some final thoughts. The traceroute checklist. If you're working with traceroute, if you're working on a traceroute ticket, if you're trying to figure out what's going on, if someone has sent you a traceroute in any way, you should always ask for traceroutes in both directions and real source and destination IPs. If you're going to submit a traceroute ticket, submit these two things. Don't bother screwing around with it and pretending like you know how to troubleshoot it, because it's going to confuse everyone. So we have our NOC trained to just not even attempt to process further, and no, send the source and the destination, send the forward and the reverse path, or there's no possible way you can ever make an accurate analysis. Also, be aware of people that send snippets of trace routes with missing information. It's very common for someone to think they're doing you a good thing by just cutting out the middle of a trace route and sending it to you, and it's completely useless. You really need to know the actual destination IP that it was forwarding to. And also be careful of people that do a trace route, see an IP in the middle of it, and then do a trace route to that IP, because that can have very different forwarding characteristics than the actual destination that they were looking at. So make sure you get real IP addresses, make sure you actually troubleshoot to the real IP address. If for whatever reason the real IP address is not reachable, you can try looking at the last hop that was reachable and do something like that. But just keep in mind that you are in no way guaranteed the path is going to be the same at all. And that's it. Questions? Mike? Go ahead.
My name's Chad Reed with the Apollo Group. Could you talk about the MPLS tunneling one more time? I was with you on everything until that point, and then I kind of got lost.
Yeah, so the way MPLS works is you have an LSP, you have a virtual tunnel from point A to point B within your network, and it's going to guarantee a forwarding path. It's going to, you might have, in this case, 10 hops in the middle, but what happens is this first router in San Francisco says, I know this packet is going to New York, I'm going to encapsulate it inside of an LSP, and I'm going to forward it to New York. And that's how you do complex traffic engineering and things like that. But what happens is, in the case where it's doing a traceroute packet, where it's dropping the packet and it doesn't know, so now it's dropped the packet and it's generated an ICMP, and it needs to send that ICMP back to whoever did that traceroute. It's not carrying a routing table at this point. It's only switching MPLS. So the only way that it has to deliver the packet is to put it back in the same LSP that it got it from, which is a good workaround to a tableless core, but a bad workaround for traceroute because it makes the traceroute look weird.
Sam Aldrin from Huawei. With respect to MPLS, I don't think you can actually troubleshoot the MPLS networks with tunneling mechanism. If you actually go back to Nanog 55 presented MPLS OEM tutorial, you use LSP ping and trace and retrace to actually troubleshoot the networks, because ICMP, for example, you take penultimate hop popping and you have LSP breakage between penultimate and ultimate hop. You cannot detect with ICMP because you could actually route it and figure that out. So the reason why I bring this point is, if you want to troubleshoot MPLS networks, you actually have similar kind of tool set, just like ICMP tool set, but specifically catered to MPLS networks. So you could actually, you can go back and, for the audience, they can go back and look up tutorial and figure that out.
So that's true if you're troubleshooting your own MPLS network. And this was an example. I'm saying you're an end user on the internet and some network who is not you. So say you're not AT&T and you're wondering why this latency jumps up so high. You can tell what's happening because they've configured ICMP tunneling, and thus you look at this and you don't think it's congestion in Palo Alto. You know that it's ICMP tunneling because it stays the whole way through. Yes, if you're troubleshooting your own network, you should use different tools like LSP ping and things like that. Right. This is talking about a third party that's just looking at a traceroute result.
Sure. So one additional question. So have you thought about the multicast traffic? How do you want to troubleshoot that?
What about it?
Because most of the things you're talking about the traceroute with respect to unicast, right?
I've not touched the multicast side of it. My condolences if you're stuck doing a multicast traceroute. Yeah, sorry, no idea.
Okay, thanks.
Any other questions?
My name is Chris Pfaff. I'm from Microsoft on the core group. So we can look at the traceroute and we can see 74 milliseconds all the way through until it stops at AT&T. Now, assuming we didn't have a verbose DNS server there, or DNS naming convention, how would we know where the MPLS tunneling stops? Because we can see that, but we have a very small millisecond increase from 9 to 10.
So one of the things I almost threw in here, and I didn't get around to doing it, is there's actually extensions to the ICMP TTL exceed messages that encode something about the LSP. And most routers are aware of this. So if you do a trace route through someone else's MPLS network, you'll get back a little message that says this went through an LSP, and it'll tell you how deep in the stack it was. It'll give you an LSP ID, things like that. So you can use that to kind of figure out if you're inside an LSP or not. But I just didn't have time to mention that here.
Cool, thank you.
Hi, I'm Adrian Soplano. I'm with AT&T, and my domain is security. So in AT&T, we debated a lot about when we went MPLS, whether to hide the core or not. And we ended up with kind of a mixed bag where we have our domestic core. As you can see, we can see the hops. But in our international core, we hide the hops. So you can only see the beginning and the two Ps at either end of the path. What do other providers do about this? And anybody thinking about hiding the core, usually for security reasons, because it's a security best practice to not interact with the core, not allow transit traffic to interact with the core in a way like TTL Exceeded does. And certainly the vendor has been recommending that for quite some time, and it will probably end up being on like security auditors checklists at some point, like many other things.
Yeah, certainly a lot of people will just turn off the TTL decrement, so like you said, you don't see this at all. The LSP is treated as though it was one single hop, and so you don't have a router in the middle dropping it, exposing itself. Yeah, that's very good at hiding that type of stuff from Traceroute. There's lots of other ways you can get around that. There's lots of, like if you poke and prod at different networks, for example, if you can guess someone's loopback address, oftentimes you'll find you don't have a way to hide those LSPs, and you'll still be able to kind of poke and see the hidden core. So I wouldn't really look at it from a security perspective. I'm personally of the mindset that I like exposing the core because I want customers, I generally work with smart customers, and I kind of want them to know what's going on and what's happening, and kind of show exactly where and why the packet's going. But yeah, you just remember that anything you see in Traceroute, you are in no way guaranteed to know that the fiber path just doesn't go via a switch network that's completely invisible, or inside an LSP that's hiding 17 different router hops, or anything else. You're at the mercy of what's exposed to you.
Okay, thanks.
Any other questions? No. Thank you very much.